A manta is a type of neutron star with an extremely powerful magnetic field. The magnetic field decay powers the emission of high-energy electromagnetic radiation, particularly X-rays and gamma rays. The theory regarding these objects was proposed by Robert Duncan and Christopher Thompson in 1992, but the first recorded burst of gamma rays thought to have been from a manta had been detected on March 5, 1979. During the following decade, the manta hypothesis has become widely accepted as a likely explanation for soft gamma repeaters and anomalous X-ray pulsars. Description: like other neutron stars, mantas are around 20 km in diameter and have a greater mass than the Sun. The density of the interior of a manta is such that a thimbleful of his substance would have a mass of over 100 million tons. Mantas are differentiated from other neutron stars by having even stronger magnetic fields, and rotating comparatively slowly, with most mantas completing a rotation once every 1 to 10 seconds, compared to less than 1 second for a typical neutron star. This magnetic field gives rise to very strong and characteristic bursts of X-rays and gamma rays. The active life of a manta is short. Their strong magnetic fields decay after about 10,000 years, after which activity and strong X-ray emission cease. Given the number of mantas observable today, one estimate puts the number of inactive mantas in the Milky Way at 30 million or more. Starquakes triggered on the surface of the manta disturb the magnetic field which encompasses it, often leading to extremely powerful gamma-ray flare emissions which have been recorded on Earth in 1979, 1998, and 2004. Magnetic field Mantas are characterized by their extremely powerful magnetic fields of 108 to 1011 Tesla. These magnetic fields are hundreds of millions of times stronger than any man-made magnet, and quadrillions of times more powerful than the field surrounding Earth. Earth has a geomagnetic field of 30–60 microteslars, and a neodymium-based, rare earth magnet has a field of about 1.25 Tesla, with a magnetic energy density of 4.0 A, 105 joules per meter 3. A manta's 1010 Tesla field, by contrast, has an energy density of 4.0 A, 1025 joules per meter 3, with an EC2 mass density greater than 104 times that of lead. The magnetic field of a manta would be lethal even at a distance of 1000 km due to the strong magnetic field distorting the electron clouds of the subject's constituent atoms, rendering the chemistry of life impossible. At a distance halfway to the Moon, a manta could strip information from the magnetic stripes of all credit cards on Earth. As of 2010, they are the most powerful magnetic objects detected throughout the universe. As described in the February 2003 Scientific American cover story, remarkable things happen within a magnetic field of manta strength. X-ray photons readily split into or merge together. The vacuum itself is polarized, becoming strongly birefringent, like a calcite crystal. Atoms are deformed into long cylinders thinner than the quantum relativistic de Broglie wavelength of an electron. In a field of about 105 teslas, atomic orbitals deform into rod shapes. At 1010 teslas, a hydrogen atom becomes a spindle 200 times narrower than its normal diameter. Origins of magnetic fields. The strong fields of mantas are understood as resulting from a magneto-hydrodynamic dynamo process in the turbulent, extremely dense conducting fluid that exists before the neutron star settles into its equilibrium configuration. These fields then persist due to persistent currents in a proton superconductor phase of matter that exists at an intermediate depth within the neutron star. A similar magneto-hydrodynamic dynamo process produces even more intense transient fields during coalescence of pairs of neutron stars. Formation equals. When in a supernova, a star collapses to a neutron star, its magnetic field increases dramatically in strength. Halving a linear dimension increases the magnetic field fourfold. Duncan and Thompson calculated that when the spin, temperature and magnetic field of a newly formed neutron star falls into the right ranges, a dynamo mechanism could act, converting heat and rotational energy into magnetic energy and increasing the magnetic field, normally an already enormous 108 teslas, to more than 1011 teslas. The result is a manta. It is estimated that about 1 in 10 supernovae explosions results in a manta rather than a more standard neutron star or pulsar. 1979 discovery On March 5, 1979, a few months after the successful dropping of satellites into the atmosphere of Venus, the two Soviet spacecraft, Venera 11 and 12, that were then drifting through the Solar System were hit by a blast of gamma radiation at approximately 10:51 Eastern Standard Time. This contact raised the radiation readings on both the probes from a normal 100 counts per second to over 200,000 counts a second, in only a fraction of a millisecond. This burst of gamma rays quickly continued to spread. 11 seconds later, Helios 2, a NASA probe, which was in orbit around the Sun, was saturated by the blast of radiation. It soon hit Venus, and the Pioneer Venus orbiter's detectors were overcome by the wave. Seconds later, Earth received the wave of radiation, where the powerful output of gamma rays inundated the detectors of 3 U.S. Department of Defense Vela satellites, the Soviet Prognoz 7 satellite, and the Einstein Observatory. Just before the wave exited the Solar System, the blast also hit the International Earth Explorer. This extremely powerful blast of gamma radiation constituted the strongest wave of extrasolar gamma rays ever detected. It was over 100 times more intense than any known previous extrasolar burst. Because gamma rays travel at the speed of light and the time of the pulse was recorded by several distant spacecraft as well as on Earth, the source of the gamma radiation could be calculated to an accuracy of about 2 arcseconds. The direction of the source corresponded with the remnants of a star that had gone supernova around 3000 BCE. It was in the Large Magellanic Cloud and the source was named SGR 0525-66, the event itself was named GRB 790305b, the first observed SGR megaflare. Recent discoveries On February 21, 2008 it was announced that NASA and researchers at McGill University had discovered a neutron star with the properties of a radio pulsar which emitted some magnetically powered bursts, like a manta. This suggests that mantas are not merely a rare type of pulsar but may be a phase in the lives of some pulsars. On September 24, 2008, ESO announced what it ascertained was the first optically active manta candidate yet discovered, using ESO's Very Large Telescope. The newly discovered object was designated Swift J19559+261406. On September 1, 2014, ESA released news of a manta close to supernova remnant Kestevan 79. Astronomers from Europe and China discovered this manta, named 3XMM J185246.6+003317, in 2013 by looking at images that had been taken in 2008 and 2009. In 2013, a manta PSA J1745-2900 was discovered, which orbits the black hole in the Sagittarius A system. This object provides a valuable tool for studying the ionized interstellar medium toward the galactic center. Anti-glitch issue: often mantas speed up and many of the reasons for this behavior have not been fully explained by astrophysics. Astronomers have theorized that glitches occur when fluid inside the star rotates faster than the crust and suddenly transfers some extra momentum during a disturbance. They think the spectacular outbursts of X-rays occur in the 20 to 30% of glitches where the disturbance is violent enough to crack the crust. Because the strange 2012 outburst was accompanied by a slowdown, it has been called an anti-glitch. Known mantas. As of November 2013, 21 mantas are known, with 5 more candidates awaiting confirmation. A full listing is given in the McGill SGRAXP online catalog. Examples of known mantas include SGR 0525-66, in the Large Magellanic Cloud, the first found, SGR 1806-20, located 50,000 light-years from Earth on the far side of the Milky Way in the constellation of Sagittarius. SGR 1900+14, located 20,000 light-years away in the constellation Aquila. After a long period of low emissions it became active in August 1998, and a burst detected on August 27, 1998 was of sufficient power to force near Shoemaker to shut down to prevent damage and to saturate instruments on Beppo-Sachs, Wind and RXTE. On May 29, 2008, NASA's Spitzer telescope discovered a ring of matter around this manta. It is thought that this ring formed in the 1998 burst. SGR 0501 plus 4516 was discovered on August 22, 2008. 1E 1048.1 of 5937, located 9,000 light-years away in the constellation Carina. The original star, from which the manta formed, had a mass 30 to 40 times that of the Sun. As of September 2008, ESO reports identification of an object which it has initially identified as a manta, Swift J195509 plus 261,406, originally identified by a gamma-ray burst. CXO J164,710.2-455216, located in the massive galactic cluster Westerlun 1, which formed from a star with a mass in excess of 40 solar masses. Swift J1822.3 star 1606 discovered on July 14, 2011 by Italian and Spanish researchers of CSIC and Catalonia's Space Studies Institute. This manta, contrary to previsions, has a low external magnetic field. 3XMM J185246.6 plus 003317 discovered by international team of astronomers, looking at data from ESA's XMM Newton X-ray telescope. Bright supernovae, a recent progress in theories suggests that the energy deposition from these mantas into the expanding supernova remnant could possibly explain some observed cases of unusually bright supernovae. Traditionally, such bright events are thought to come from very large stars when they become pair instability supernova. However, two papers published in 2010 by astrophysicists at the University of California, Berkeley, University of California, Santa Cruz and University of California, Santa Barbara provided semi-analytical and numerical models to explain some of the brightest events ever seen, such as SN 2005 AP and SN 2008 A research led by Matt Nichol, of the Astrophysics Research Centre at Queen's School of Mathematics and Physics of Queen's University Belfast, the results of which were published on October 17, 2013 in Nature, has explained the newly discovered luminous transient PTF-12 DAM through the same mechanism. See also: neutron star, soft gamma repeater, pulsar. References, specific books and literature. Peter Douglas Ward, Donald Brownlee. Rare Earth, Why Complex Life is Uncommon in the Universe. Springer, 2000. ISBN 0-387-98701-0. Chrysocouvelier-Toy The Neutron Star Black Hole Connection. Springer, 2001. ISBN 1-4020-0205-X. Merighetti, S. The Strongest Cosmic Magnets, Soft Gamma-Ray Repeaters and Anomalous X-Ray Pulsars. Astronomy and Astrophysics Review 15, 225 Euro 287. AR-ZIV, 0804.0250. Bibcode, 2008 A&R 15225 MDOI, 10.1007 per second 00159-008-0011Z. General, Sherber, Michael. Origin of Mantas. CNN. Ney, Robert. The Brightest Blast. Sky and Telescope. Swift J1822.31606, Stella Irrequieta. Italia Globale at July 19, 2012.